It is my pleasure to have Ching An Cheng here, visiting us from Georgia Tech today. He's a PhD student, finishing in about a year. He's doing super cool research at the intersection of machine learning, control, so imitation learning, reinforcement learning, and so on. Specifically, it's a very cool combination of theory. He got best paper at AI Stats this year, and practice, where he's deploying his approach on actual robots, rovers, and he got a best systems. He was a best systems finalist at RSS this year, the robotics conference. Anyway, so with that, without further ado, I'm going to hand it over to Ching An.
So hi, good morning. So thanks for having me here. So today I want to talk about my recent research in policy optimization, and specifically on the idea of treating policy optimization as predictable online learning problems. So this direction of research is motivated by our research in imitation learning, but we recently go beyond that and trying to further extend that to also to reinforcement learning, also beyond in other optimization problems. So if we go into details, let's talk a little bit about myself. So I'm currently a fourth-year PhD robotics student in Georgia Tech, advised by Byron Boots. So my general research interest lies in the intersection between machine learning, optimization, and control theories, and the goal is trying to build more efficient robot learning algorithms with theoretical foundations. Right. So my current research are three parts. So the first one concerns RL and imitation learning, about just trying to build up algorithm to learn policies. And the second part is about trying to use very large-scale Gaussian process to model uncertainties, and let's say with the linear complexity. And the last part is about the control and planning side. I want to design algorithms that can combine the best part of planning and control and their properties together in a single framework. So, and today I'm going to talk about an online learning approach to policy optimization. So in online learning, as we probably know, it's a framework to analyze online decision making. The way it works is that it's a repetitive process. So in each iteration, let's say the learner makes a decision pi n out of a decision set capital pi. And in the policy optimization context, pi n will be the policy that the learner currently have, and capital pi will be the class of policies. And now once the learner chooses that policy, it will run that in the environment, and the environment will returns a cost function, loss function, Ln. And that can depend on the pi n which the learner chooses. And so when the loss function is determined, then the learner will suffer a scalar loss function. And at the end, this will repeat for many iterations. And at the end, we care about bounding the performance in terms of the accumulated loss that the learner suffers, the sum of Ln of pi n. And then, because in general, this Ln can be adversarial, so probably we can only bound the regret in terms of this accumulated loss. So we're just comparing that versus like, the best decision that you can have chosen in the hindsight. Right? So what do I mean by policy optimization as online learning? So on the left-hand side, we have the policy optimization problem, like training a policy to do some job that we want to solve. On the right-hand side, we have the theoretical framework for online learning. So in here, policy optimization has some objective function. So in order to convert that to online learning, we need to define what we want to have as a loss function in the online learning. And once we have that loss function, we might know some property about those functions. And then we're going to design some online learning algorithms. And we're going to use that. And then we're going to use the technique that we know about online learning to analyze that algorithms. And then at the end, we get some performance bounds about the policy optimization process that we care about at the end. So it's like converting policy optimization to online learning by some proper conversions, and then solve it there, and then bring the performance back to the original problem. So the thing I will talk about today is that the first one, I will review the classical reduction that we have from imitation learning to adversarial online learning problems by Stephen Rose et al. And so the second part is that I will actually argue imitation learning is not adversarial. So the previous reduction actually lost some information, and it's not optimal. And then this leads to the idea of using prediction to make it better, so to make it better in terms of analysis and also in terms of designing better algorithms. And the last part is that I'm going to present a reduction framework. It's called PicCOLO. So it's a general reduction framework to convert predictable online learning problems into adversarial ones, and so you can use standard technique for adversarial learning to solve that ultimately. And that can be applied for imitation learning, RL, and even beyond those scenarios. So let's go to policy optimization. So policy optimization, in here we care about solving a reinforcement learning problem. So we want to find a policy pi that has good performance in terms of some loss function j of pi. And here that j of pi, for example, can be defined as the average of the expected accumulated loss, and where the expectation is taken on the trajectory distribution generated by rounding the current policy pi, right? So this is a finite horizon like RL problem, but you can extend the same techniques to infinite horizon one as well. So the way we're going to abstract this problem is that we're going to exchange the order between summation and expectation. So now we can define a more abstract or generalized version of average state distribution. So basically what it says is that the loss function that I want to minimize is the expectation of the instantaneous cost over the state and action distribution generated by the policy. So here I have two important parts. So the policy will generate the state that it visits, and also policy will generate the action that it wants to take at the particular states. This is the cost function that I want to minimize. So why do we want to consider imitation learning? So the main reason is because RL is just too hard to solve in general. And also because RL is not the problem that I want to solve, let's say for robotics. For robots, let's say we want the robot to achieve some task. RL is purely a mathematical formulation that we have about this process. And this is not we are not solving that mathematical problem in our application. This is just a way to frame that problem. So if you're thinking like that, we actually have more information about the application of the problem that we actually care about. So we have this prior information. So imitation learning is trying to use this prior information to speed up policy learning in the form of the expert demonstrations. So this expert can come in many, many different forms. A common expert can be like human demonstrator, which we know about like the task I want to solve. Let's say you want the robot to grab a cup, you can demonstrate how to grab the cup yourself. But another type of expert are algorithms or heuristics, because we have been doing research in AI for many, many decades. So if let's say we simplify the function a little bit, let's say we remove some constraints or we add more sensors, now it might become a problem that we know how to solve. Right? If let's say we discretize the world and just make the state space even smaller, we can actually do planning optimally. Right? So this kind of heuristic actually can be used as another form of expert in order to speed up policy learning for the original problem that we care about. So the goal of imitation learning is trying to minimize the performance difference between the learner's policy and the expert's policy. And by performance difference lemma, this can be written as an equality. And so the difference will be equal to the expectation of the advantage function with respect to the expert policy and over the state and action distribution generated by the learner. Right? So because the advantage function basically measures how an action is better than the expert policy on that particular state. So if you take the expectation over the state and action pair given by the learner, then basically it tells you the performance difference. Right? So imitation learning will be trying to minimize the thing on the right-hand side. But usually we don't have the advantage function directly. So we might want to minimize its upper bound instead. So let's say we have another distance, some sort of like general distance function between two policy, pi and pi star. So we can upper bound this gap with a constant times the expectation of that distance function over the state visited by the learner. So now we have a problem that we potentially can solve. But what is this problem? So in this problem, we first have to define this distance function. And there are many ways to do that. For example, you can use an estimation of that advantage function, for example, or you can use, let's say, the action difference, let's say, the square loss between learner and the expert's action. Or you can use KL divergence because we are minimizing statistical distances. Another thing that people can also use is that you can use an adversarial trained neural network to learn how the loss function, so that it works in a more robust setting. Right. So there are many ways to choose that D, and then you will get a different constant C there. But this is still an RL problem. And the main reason for that is because in here, we are still considering the state distribution as a function of our policy. So let's say we want to take the gradient, you have to consider the backpropagation through the dynamics. And that's a difficult part. So although this problem might be easier than the original one, let's say the original problem have a cost function C, and that might be sparse. But we define this D function, which might be dense. So this is an RL problem. So we define upper bound, we get a new RL problem, but that might be easier, but it might be still very hard, let's say, for robots, because you have to interact a lot with the environment. So another way to further simplify this is that because we know the difficult part comes out of that state distribution. So let's assume that's going to be fixed regardless of how we change the policy. So what we end up having is that let's say we have some policy pi n, and we get some state distribution, and assume that's fixed. And we just optimize the part that's independent of the state distribution. And now we have this loss function that's very easy to optimize. It's almost like statistical learning. But there must be a cost in here, right? We must have some drawbacks. The price that we take is that originally the RL formulation is a global upper bound of the performance difference, but now for this one, it's only a pointwise upper bound, which only holds exactly at the pi m policy, which is the one you define as the distribution. So what it means is that if you minimize this loss function directly, it will not ensure you to minimize the performance difference, because it only holds at a particular point, not the entire policy class. So we cannot use that as a superascending cost function. But we can actually use that as an online loss function, because the thing on the right-hand side in the upper bound is actually the loss function that we want to bound in online learning. It's exactly the sequence of loss function that we have in online learning when we're designing that regret, for example. So we can use that as an online learning problem, loss function. So now let's treat that as an online learning loss function. And the classical algorithm that we can use, that probably the first one you will know in online learning, is follow the leader. Right. So if you apply this idea in imitation learning about the loss function that I defined, and that will lead to the very classical algorithm, also very practical in practice, I'll call data aggregation or value aggregation. So a stagger or aggregate, which we might heard. So what it does is just using that loss function and just to follow the leader, right? And the way it works in practice is that you have some policy, you use that to run the policy in the environment, you collect some samples, you define that loss function for this iteration, and then you use that all the loss functions together, and then you update the policy by minimizing the sum of them. And you do this again and again and again, and then at the end you have some policy sequence, and that might be nice. So because this is just a very classical algorithm, so we have very simple analysis. So if we assume that every loss function is strongly convex and Lipschitz, which is nice, the nice thing that we can have, then of course we can get this standard analysis convergence in online learning. So you see that using that inequality and combined with the regret analysis in online learning, we get performance bound in the policy sequence, which says that on average, this performance sequence will converge to the expert performance plus in a rate of, let's say log n over n, and plus some tiny epsilon. And the epsilon captures how expressive this policy class is. And this is the minimum that you can achieve by minimizing all these sum sequences. So basically, some tells you that how your expert, whether there is a policy in your policy class that can imitate the expert well almost globally. So for example, if your policy class contains the expert policy, then epsilon will be 0, then which means that eventually it will converge close to the expert performance after some iteration on average. So we can, of course, we have followed the leader, but we also have a bunch of first order algorithm in online learning where you can take gradient descent or mirror descent or follow the regress leader. So if you do that, go to some other algorithm imitation learning like aggregate or daggered, and of course just the standard online learning techniques, so you get a similar performance bound. So if you visualize that a little bit, so what it does is that you have a cat agent trying to imitate a lion expert, and the behavior you have here is on average. So you might, let's say the blue curve is the loss function of the RL problem, and then you might get some oscillation in between, but eventually you will converge close on average to the expert's performance. So the benefit, let me summarize. So online learning approach to imitation learning allows you to use optimal experts as a demonstrator, so to speed up policy learning. And we can show that especially when the expert policy is not trivial, let's say it's just better than a random policy that you will have, let's say, when you randomly initialize a neural net, then it will converge faster than RL. And the main reason is because in here, it minimizes the relative performance gap. So it's invariant to the absolute scale of the original problem. So you're basically cutting the performance gap based on the difference, and in some fixed rates almost. And another reason is because the gradient you use in imitation learning is much less noisy and doesn't have much bias. So in here, you ignore the state distribution change, so you don't have to do that very complicated part. And also in here, you don't need to estimate the value function. You have some D function, which you might know how to take derivatives, so you might be able to take analytic gradients, for example. So that's why it converges faster, a lot faster actually. But so everything seems very nice. Okay.
To get that, so do I need to have access to the expert's policy pi star in some parametric form?
No. So you only need to treat that as a black box function, so that you can just query the demonstration for a particular state.
And even that is able to give us low variance, low bias gradients?
Yeah. Yeah, because the main reason is because in RL you need to estimate the value function or the advantage function, right? And that's have a future. And because in here we are ignoring the derivative through the state part. So you don't have that accumulated part. You only care about the instantaneous one. So that's the main reason why it has a very nice gradients compared with RL. Yeah, so feel free to interrupt me if you have questions.
So does your setting apply to the setting where you only have finite number of expert demonstrations, not really a black box function you can query theoretically infinite many times?
Oh yeah, so it's very nice in the sense. So in that setting, so in some sense, let's say you have human demonstrator. Let's say it's not very convenient for you to just query ask questions,
Yeah.
and you can do the just like the more standard like behavioral cloning one, and you get similar properties, but theoretically it's worse than this online interactive version, but it might still be better than the RL part. It is at the beginning of learning. Because at the end, you will see the suboptimality of the expert because you cannot perform better than that. And also convergence in the later on will be slow. So, but at least at the beginning of if you compare the performance, you get number of examples that you have in imitation learning versus the number of experience that you have to interact with the environment in RL. That part, the imitation learning one will be faster. Yeah. So, but the question is that now this is the algorithm that we have been using for years, at least 10 years at least. But can we do better than that? So in order to think about this problem, let's revisit the reduction. Sorry.
Can I ask another question?
Yes, sure.
So in your framework, can you do better than the expert?
Oh, so if you want to do, we can discuss maybe later. So I have gone back outside. So the general idea is that if you want to do better than expert, you need to have some sort of signal from the loss function you care about in RL. If you somehow mix the gradients or mix the function together, or let's say do imitation learning and switch to RL in some sense like that. So you have some signal from that, then you can do better than the expert and still much faster than RL alone. Yeah, we can talk about that offline if you want. Yeah, so can we do better than what we can do right now, right? So let's revisit what we have done using that reduction idea, that 3 step that we have. So we define loss function, algorithm, and then performance bound. So in the current setting, we have the loss function, which is our performance in RL, right? And we reduce that into this online loss function by ignoring the change of state versus the policies. And now we design algorithm, use optimal algorithm in the online learning literature for that setting. And we also use the optimal regret bounds that we have, up to a constant, of course. And so everything is optimal. So what can we improve? And the thing is that these are only optimal when the problem is adversarial. Right, your gradient descent is only optimal when the loss function is changing arbitrarily, and in that sense. But what if the problem is not optimal, right? Is the loss function that we have is actually optimal? I mean adversarial. Sorry. So here I'm going to argue why that's not adversarial. So the first thing is that if you look at this loss function, the thing inside the expectation is the same for every iteration. You are trying to learn from the expert. And in most of the settings, the expert is not going to react adversarial to you. You might have that scenario, but probably that's not the case you want to apply imitation learning. So that part is not very bad. You're either the expert is the same or it's trying to be nice to you, right? And also the other part is the state distribution. So in online learning, we are treating, in the previous reduction, we are treating that as arbitrary component that might appear in this online loss function. But that state distribution actually comes from the same MDP process. We are not changing the robot to, the environment is not going to react adversarially to our policy change. That might be true in other cases, let's say in some game, for example, but not usually in the case we care about. So that part has some kind of continuity that we can leverage, right? So some ideas I hope they convince you that this loss function is not completely adversarial, but actually can be predicted using past informations. For example, if you interact with the environment, you see some state transition pairs. You have some knowledge about the dynamics, which lets you can help you to predict the loss function. And for example, you can even query the expert, let's say in simulations. Then the thing inside the expectation is actually known to you. So that part is not really adversarial. So this is actually still an online learning problem, but it's a predictable online learning problem where the loss function can be predicted from the past in some form, at least partially. Okay.
So I was wondering, so if the expert is trying to, they're not being adversarial to you for the sake of being adversarial, but they're basically trying to, or if they're trying to teach you by kind of leading you to parts of the state space, regions of the state space, where they think you're not doing well.
Yes.
Is that considered adversarial in some sense?
So it really depends. I think this where we don't have much theory about. So currently most of the learning are assuming that the expert have a fixed distribution. You can have many experts, but the distribution is fixed, and that doesn't change with the learner. And also the policy doesn't change with the learner. But it's interesting to actually think this rather than as a single player online learning problem, but also as maybe a collaborative game. For example, you have expert and learner trying to do well together so the learner can learn well. And it's interesting to in that scenario, I think there are some few papers about that. And that's also like applicable when you can design the expert yourself. But that scenario becomes kind of awkward in the sense that when let's say your expert is a human demonstrator, and they think he's trying to help you, but it's actually hurting you. And that's where the theory becomes vague. Yeah. But in here, I'll assume that let's say the expert is just fixed for now. Yeah. So now this is our previous diagram. But if now things become predictable, the algorithm and the bounds that we have are no longer optimal. So now this become question marks. How do we design algorithm for this setting, and how do we do analysis? Okay, so for the rest of the talk, I'm going to talk about two parts. So first part is trying to have a better analysis for the previous algorithm, like let's say follow the leader in dagger or aggregate, by using the fact that this loss function is predictable in some sense. And the second part is to design a better algorithm that use that predictable information to make learning faster. Okay, so let me talk about the first part. So this is my AI stats paper this year. And so the main motivation is that there's a gap between theory and what we do in practice, actually. So in theory, for online learning, their analysis, it tells you that we have an average convergence, right? It doesn't really mean that the last one is the best one. So what it means is that you can either randomly stop the sequence, and that might, on expectation, give you the one that you want, or you need to keep all the sequence and at the end identify the best one among them, and that will have the thing you can have guarantee on, right? But as a practitioner, and probably the thing you will implement is just run dagger for memory iteration and just stop. And that number of iteration is not chosen randomly, just something you think that's like, let's say your paper are doing a week, that's the number of experiments that you can do, and that's your budget. You just run it and then stop. And then you use the last policy as the one that you think that's the best one. And the intuition is because you are thinking the last one is trying on more data, so potentially it should be the best one, right? But is this really true even in practice? Does a policy actually improve monotonically, let's say when you do more iterations of dagger or aggregate? And if you look into different papers, you'll find different answers. So if you look into Ross's paper, like the one who proposed that, you find yes, you become better and better, and actually in our experiments as well. But there are other papers which can construct like artificial, actually like real cases where this is not true. Like the error can increase when you do more iteration of dagger. And most of the time, this is because there's a gap between your policy class and the expert's policy. So if that's true, then this is more likely to happen. But if that's not the case, then usually you might see the other one. But it depends. Yeah, and then the main result that we have in this paper is that we actually can show the convergence of the last policy of this like follow the leader idea theoretically, and we have a condition and a bound for that, right? So, and this is only feasible when we know the problem is predictable, because in general adversarial analysis, there's no way for you to show the last convergence for any sequence. And so here we're going to use the fact that we're defining the loss function like this. So the way we're going to characterize this structure is that we're going to define a bivariate function, a function with two arguments. So the left argument of the capital F, that function, is going to be the policy that determines the state distribution. And the argument on the right will be the one that you put into that distance function. Right. So if you compare this definition with the definition of the loss function that we have, you will see that Ln is just actually just putting pi n on the left argument. And if the gradient that you see when you do like learning with these online learning parts will be just taking the partial derivative of this capital F. Right. So now we have maybe a better way or more close way to describe the loss function that we have. And now we're going to make some assumption, some reasonable assumption, and that can give us more information about what actually involved in the policy learning process. So the information that, the assumption that we're going to impose is on how fast the gradient that we see from online learning is going to change when we change the policy that's used to collect the data. So we see that the partial derivative corresponds to the gradient that you were seeing in online learning, and now this inequality basically says that it's going to be continuous in the policy that you use to collect data with some Lipschitz constant beta. We're going to talk about what that is later. All right? So what we show is that there's a single stability constant which we call theta, which is the ratio between beta and alpha is, let's say, the strong convexity of the online loss function. So you can think that the convexity will provide stability, but if beta is large, let's say the gradient changes a lot when you just perturb the policy a little bit, which means that the problem is very sensitive, then it becomes unstable. So we show that when theta is less than 1, if you just run Dagger or aggregate, you always converge. The best one, the less policy will be the best one. But if beta is larger than 1, there are some cases where it will always diverge. Right? So the first result that we have, yes?
Just a clarification. So this has nothing to do with the complexity of the policy class. It has more to do with the dynamics of
Exactly,
the system.
yes.
Okay.
Yes. So the first result that we have is a convergence, a upper bound on the performance of the last policy. And this bound is actually non-asymptotic, and we just simplify that in these slides. And then so what happens here, we show the last policy is bounded by the expert performance plus some epsilon plus n to the 2 times theta minus 1. Right. So if you see that if theta is less than 1, then the thing on the blue box will converge to 0 at the end. And that implies a conversion when theta is less than 1. And here the delta epsilon is a little bit different from the previous epsilon, as I'll explain. So here delta epsilon is the minimization that you can, the minimum value that you can achieve for a single loss function. If you compare with the previous one that you have, the previous one is about on average convergence, and the previous epsilon is about the minimum that you can achieve among a set of loss functions on average. So you can imagine that if your policy can only imitate the expert locally, then the new delta epsilon will still be small, but the first epsilon that you have in Dagger might be very large, because there might not be a good policy that can mimic the expert globally on all the states that it visits. So here you have a bound that's interesting in the sense that it's dependent, it's tighter in the sense that it have a epsilon that describes the thing you might care about more in practice. And on the other hand, you have the previous epsilon, which is a little bit too conservative. And also we have a convergence rate that's dependent on kind of like the difficulty of the problem. So we can actually show there's a lower bound which matches the rate of the upper bound, and so that's why this convergence in terms of the order to theta is tight. We cannot improve that unless we have further information about the problem. And this is even true when the policy class capital contains a global optimal policy for the RL problem or the imitation learning problem. So this is, I think, a very strong result in some sense. But this is kind of sad because we are showing what we show is that we have some problem, and its dynamics determines that theta, right? We don't have any control of what theta is. And given that dynamics, we have some hard problem where basically we're saying that rounding Dagger will always diverge, for example. And some problem is nice, right? We don't have any control guarantee about whether we want to use the less policy or try to keep all of them, right? And it's kind of sad. But it turns out that we can actually stabilize the problem by adding regularization. So if we change the problem a little bit by adding regularization to the loss function, then for this new problem, we can have an effective new delta theta, and that's going to be less than 1 if you add enough regularization. Which means that if you solve the new problem, then it will always converge, and at the end, you can just pick the less policy without really doing that stuff.
So just again to make this completely clear. So even if you have the policy class that the learner is using contains the policy of the experts, the diagram can diverge.
Yes, in some weird case.
But then how? So the proof from Ross from the 2012 paper. How then? There seems to be a contradiction.
Oh, there's no contradiction. So the thing hides into that epsilon. So in that case, the epsilon will be very large for the original formulation. That can diverge, and epsilon will go to infinite. Also, here is a little bit different. So here is like pi contains a globally optimal policy for that imitation learning process, but that might not be the expert policy. So the way we construct this counterexample is that the policy class of the expert is different from this policy class.
Okay.
But there's still a policy in this policy class such that it gives you 0 imitation learning error.
I see.
Yeah. So we don't know whether this is true when this policy class contains exactly the expert policy. I think that's not true. As long as that's the case, this epsilon can be 0 for that scenario. But in general, you don't know whether that's true or not. So let's say there's a difference between, let's say the expert is just not strictly inside your policy class. And for that case, we can construct a problem where it will diverge. But still, this policy class that we actually have a global policy, and it can be actually solved in linear time, which means that converge exponentially fast if you just take gradient. Do gradient descent with the original RL problem, the RL problem that I formulate with the upper bound. So does it answer your question? Yeah. So details hiding to the epsilon. So I'm going to talk about 2 approaches to stabilize the problem. So the first one is actually a way to justify the heuristic that Stephen Ross originally proposed in their Decker paper. So in the online learning problem that we talked about, we are saying that the loss function for each iteration is defined using the current policy, right? But in fact, that's not usually the case that we do. What we do in practice is that when we collect the data, we're going to run a mixture of the current policy and the expert policy. And in the original proof of their paper, they don't provide a constructed reason. They just say that when you do this, it will not hurt the regret bound. So it doesn't tell you why you should do that. And here is an explanation of why that makes sense. So what we show is that if you mix the policy together, and let's say you have so each time step you have some probability to use the expert policy instead of the current policy to collect the data. And let's say we call that a mixing rate. So we are saying that if the mixing rate is high enough, which means that you are going to, with high enough probability, you are going to use the expert policy to collect data, and the new problem will have a delta epsilon that's going to be less than 1. Because you can imagine that when, let's say, the mixing rate is just 1, always use the expert policy, then you have a supervised learning problem, right? And it's always stable. But you have a cost. You will have an additive constant cost there. And that one is going to be proportional to the mixing rate that you're going to use the expert policy. So that will be maximized, let's say, if you always use the expert policy. So the higher probability you put on the expert policy, because you're going to see a different distribution than the one you're going to visit, then that constant bias will be larger. But if you properly choose that, as long as that's larger than some threshold, then the problem will be stable, and the constant might be a little bit smaller. So that's one way to stabilize the problem, and it justifies the heuristic that people have been using. Right? So another way to stabilize the problem is actually better. So the way it works is just that previously let's say we have the online loss function for imitation learning, and that's collected under the current policy. And now let's say we consider a new online learning problem where the online loss will be the original loss function that we defined for the online learning, plus the loss function collected under the expert policy times and weighting on that. You just add the one, so the cost on the right-hand side is the thing you would do in the supervised learning approach for imitation learning. You just add them together and plus some weight, times some weight, right? And this is actually being used in the literature, especially from people, by people from Berkeley. So I have some empirical paper about basically just mixing the gradient together and then apply that on robots, right? So we show that if the weight is larger than some threshold, which is problem dependent, of course, and we don't know how exactly that is, but there's larger than some threshold, then the new problem will have a delta theta that's strictly less than 1. So it will always converge. And if you compare this result with the previous one with randomized mixing, then here the cost that you pay becomes a multiplicative constant, right? So you won't have a constant bias. So you basically magnify that delta epsilon that we have, which is already smaller than the original epsilon. And then, of course, you can imagine that this constant will become larger if you put more weights on the expert part, right? So the weight go to larger, then this constant become larger. And because the reason why it doesn't have a constant bias is because in this formulation, no matter how large the weight is, you always have some component from the current policy. So you won't have the constant bias. So have some experience from the current policy. And then everything is shifted to the constant, the multiplicative constant on that. And what it means is that if you just choose, you want the problem to be stable, so you choose a large weight, for example. But you can still have better performance, just by increasing the expressiveness of the policy class. And this partially explains why this technique works with, like, let's say, the training imitation learning with like deep neural nets, right? So you add those gradients together, make problem stable, and now you are safe to say that I can use a less policy. And then the only thing I need to worry about is trying to use a policy class that's expressive enough, so that constant factor, doesn't matter that much, right? So let me summarize what I did in the analysis. So we showed that the convergence of like value aggregation or data aggregation is actually problem dependent. If you don't change the problem, it might diverge or converge. There's nothing for you to control. But if you regularize a problem, you can always make sure that we're going to converge. And that creates some way to justify the heuristic people have been used in practice, theoretically. And very recently, like actually in this year's wafer in December, there's another paper which extends this idea about trying to think about prediction about how fast the gradient will change in terms of policy, and you can show similar convergence result for the first order approach I talked about for imitation learning. If you just take gradient rather than doing follow the leader, you can show similar convergence. And it also shows that the convergence also depends on death data. Right. Okay, so that finished the first 2/3 of the talk. So then the next thing, I've mentioned that now we show using prediction, we can have tighter analysis, which might, and also explain the things that we have been doing for years, right? And so that's one thing, but it doesn't change our algorithm very much. So the next thing is that, can we use this prediction information, predictable information, to design even better algorithm that can converge faster, theoretically? So how do we do that? So for the rest of the talk, I will switch back to focus on the average convergence for now. So you might have a larger epsilon, but let's focus on that. And so the thing we're trying to think about is that, what do we actually mean by using predictable information inside an algorithm? Let's say, what kind of representation, or how do we actually construct represent predictable information in our algorithm? So to do that, let's try to get some intuition about what kind of information that we actually need when we are doing policy optimization, right? So let's consider a very idealistic scenario in online learning. Let's say in each iteration, I not only know the current loss function, there's someone else give me the next loss function. So if I have that information, I can actually update the policy by an algorithm called be the leader, which is just adding the loss function of the next one in addition to the loss function, some loss function I have in follow the leader. So I always have one step ahead. So in that case, if the next loss function is exactly the same as I will experience later on, then we'll have a zero regret. So which means that the convergence on average will just converge in one step. It's always zero. And that you solve the problem completely in one step. So this is an ideal scenario which might not be doable. So let's think about how do we actually implement this in this setting. So this is not doable at all in the general adversarial case, because you don't know the next loss function and everything can be arbitrary. This was only used to think about analysis. But in this predictable problem, this might not be feasible. So to think about that, and the reason for that is because we define this online loss function using this bivariate function capital F. And that capital F is used across all the iterations. So if we know that capital F, maybe we have a way to know the next loss function, right? Because that captures all the information that we need. And the way we do that is that we can look into the optimality condition of this update. So basically, it can written as a variational inequality, which says that the direction of that gradient of that some loss function should be in the direction of, should have like an accurate direction for all the direction in the policy sets. So you want to find a policy pi n plus 1 such that this inequality is true for all the policy in your class. That's basically the optimality condition of the argmin, right? And now to do that, we can using that condition, it actually gives us some information about how we can use that capital F to do be the leader. So if we know capital F, we can use definition that the gradient of the next loss function is equal to the gradient of the partial derivative of capital F at pi n plus 1. So now, if we put in that into this inequality, now this is actually a problem that we can solve because we know all the variables, the capital F and the gradient of previous loss function here. And if we can solve this variational inequality, then the solution that we get, and when the capital F is exact, then we will be exactly doing be the leader algorithm. So if we know capital F, and if we can solve this inequality problem, you can just think that as some sort of like equilibrium point problem, then we will be doing exactly be the leader, and we will suffer zero regret, and everything converges in one iteration. That's very nice. But in practice, we don't know about capital F, otherwise we have solved the problem. So let's think about approximation. So what do you want to approximate? So if you look at here, you use the information of this partial derivative. So let's say we have a mapping, which such that given any policy pi, it can approximate that partial derivative, right? So let's say just replace that, and then we replace that, and then put that into this variational inequality, and we solve this problem instead. So as long you can imagine that as long as that prediction is like kind of close, then you can still doing almost as well as be the leader. And in this paper, we actually show that you can actually learn that loss online and still be sufficient. But I will not go into the details. But the thing I want to tell you here is that this algorithm, which we call model-based imitation learning, but here the model is about a way to predict that partial derivative. So the model is not just dynamics model as you might thought. Here we're talking about model in terms of predictor online learning is a way of mapping that you can predict this derivative that we care about when we want to be the leader. And so we are going to call this mapping a predictive model. It's a way to predict gradient. It's a vector value mapping. In other words, that if we have a mapping, if that predict exactly, and we can solve that variational inequality to be the leader, then we will have improved convergence. But there are practical issues, right? So what we know is that this formulation suggests that there are some information that we can leverage to make the algorithm better. But that algorithm, let's say I would imagine that you don't know how to solve this one. This requires a certain iterative process to actually solve for the solution for that inequality. And it's not trivial, and it might not converge as well. So that's a practical problem. It's like more like an ideal conceptual version of the thing we can do, but probably not the one that we will go to implement on a robot. So we need to have a more practical version. So one way to come with those algorithms is that we can look into the literature of predictable online learning problems. There are already some algorithms, let's say first order algorithm in like mirror prox, optimistic mirror descent, or follow the regularized leader with prediction. And maybe we can use those algorithms to design in previous stagger, we use follow the leader. Let's say we use all these new algorithms for that specific setting and design new imitation learning algorithm, for example. Is that a good idea? But the problem about this approach, as I will argue, is that this problem is actually less well-studied compared with the adversarial literature, and they are usually more complicated. They have a nasty update rule, and usually you require certain fine-tuning on the step size for it to work. And those fine-tuning on the step size actually requires a bunch of constants which you don't know in practice. And so that makes, if for application scientists want to implement those algorithms on a robot, it becomes very, very difficult. And so in practice, let's say we are using a bunch of modification of those theoretical algorithms in practice. And so we need some adaptive algorithm that can work robustly in practice. And those algorithms should also be very easy to tune and to understand as well. And this is more like an issue, not in general predictable online learning, not just in imitation learning. So here we are reducing that to predictable online learning, and now we realize there is an actually practical algorithm that we can use in practice. And this might explain why people haven't been thinking about converting problems into predictable online learning problems, because we don't have well-studied theoretical algorithm for us there. Maybe scientists understand that, but not for other people, right? So we need something else. So our idea is to just go beyond imitation learning to think about how you should do that in these predictable online learning settings. And then later on, we have designed some reduction-based algorithms such that we can leverage the tool that we already have for the adversarial settings so that we don't have to reinvent the wheels, right? So now we can have something that's going to work robustly and going to work for most of the people. So we call this algorithm or this framework PicCOLO. So it stands for Predictor-Corrector Policy Optimization. So it's a general reduction technique for solving predictable online learning problems. So here, what it means is that it's a problem where the cost function is linear, and maybe the decision set is convex. And so the way it works is that it's going to convert, let's say, a number n iterations of a predictable online learning problems in here, where the loss function is specified by some vector gn, because that's a linear loss. And it's going to convert that into a new adversarial problems, and then just apply the technique that we know on that new problem. And I'll show that it actually works optimally. So the way we do that is that, let's say we have some predictable vector coming out of, like model gradient, coming out of our predictive model that I described earlier, right? So just add there and subtract that, and you have this equality. And to simplify the writing, let's define the difference as an error, right? And now here's a trick. You just add a new decision variable, let's say called pi n hat. Just add in here and subtract there. So what we end up having is that on the left-hand side, we will have a new adversarial problems, which have 2 times more iterations. And the sequence works like this. So you make decision pi n hat before seeing g n hat, and then you get g n hat, and then you make decision pi n, and then you see the new error en. And because in this problem, g n hat and en are not predictable at all. They are adversarial because you already subtract all the predictable information that you have from your predictive models. So this is an adversarial problem. So maybe the optimal way to solve that is just apply the optimal algorithm for that, right? But would that give you the optimal regret? You have to show another thing. It's the right-hand side. The right-hand side, if you look at that, you will see that pi n is actually made after you reveal g n hat, right? So it's actually later on. So which means that the blue box is actually negative. So what this conversion means is that for a predictable linear problem, you can convert that into a new problem. You apply adversarial technique to that, and if you show that the blue box is negative enough, then you will have accelerated convergence in terms of average regret, right? This is basically how PicCOLO works. So PicCOLO just apply a basic algorithm for adversarial setting for this new adversarial problem with 2 times more iterations. And we're going to show that this idea, although sound very trivial, is actually work as optimally as a specialized version. So you can actually apply, define this convert to this new problem, apply, let's say, aggregate to solve this one. You don't need to know anything about those specialized algorithms. And also we show that this will work for any base algorithm that can be written in the form of mirror descent or further regularized leader. And those are basically the optimal choices that you can have for adversarial linear problems. Right. So we have talked about more abstract online learning problems, predictable online learning problems, but now we want to focus back to policy optimization. So in order to do that, we have already showed that PicCOLO, not PicCOLO, but imitation learning can be written as predictable online learning problems. But now we want to go further than that. So here we're all going to show that actually reinforcement learning can also be written as predictable online learning problems by some proper choice of the loss function sequence. So if we can do that, then we can apply that technique to both imitation learning and RL, right? So the way we do that is that we're going to define a loss function on a loss function as like this. So here is equal to the expectation of the FNH function with respect to the previous policy on the state and action pair with the state distribution of the current policy, right? So it's kind of a way to measure how a policy compare with the previous policy that you have. And if you look at this loss function, which might look weird, but it's actually quite familiar. If you take the gradient of this loss function, what we'll see is the thing on the right-hand side. So the thing on the right-hand side is actually a practical version of the actor-critic gradient. So if you have recall that for the theoretical version of the actor-critic gradients, it's defined like this, but for the advantage function is with respect to the current policy, not the previous one, right? But that theoretical version is usually not the one we implemented, because in order to implement that, we need to run 2 rollouts per iteration so that the gradient we compute will be unbiased. So what we run in practice is that in each iteration, we have the advantage function or the value function of our previous policy, and we run the current policy, collect some data, we compute the actor-critic gradient. And when you compute that gradient to update the current policy, it's actually using the previous advantage function or Q function or value function. And then after that, we're going to use the same experience to update the value function estimate. Right, so the advanced function or value function that we use to implement like actor-critic algorithms is actually always one step behind. And this is exactly the gradient of this new loss function that we define for RL in this conversion. So we can actually show that the average performance of this policy optimization is bounded by the performance of the initial policy plus the regret bound and epsilon for these new loss functions and loss sequence. So here regret is defined as the sample version of that loss function. So this delta Ln is equal to the sample version of that kind of like actor-critic loss function that we have. And so here is a regret. And here the epsilon is it's like the one we define for imitation learning. It's like the minimum that you can have for that sequence of loss function. So suppose now we have a no regret algorithm, which means that this regret is going to be sublinear. Then the turn on the left turn in the expectation was going to be less than order 1, right? But now if this epsilon is always more than negative order 1, then this term will become -1, which means that on average, you're going to improve roughly the same as number of iterations that you have. But there's some details we can discuss offline about, let's say, how large the epsilon actually is. Like we see the problem of like having super large epsilon in some worst case problems, right? But this part has to be worked out, and then we can talk about some ideas about that later on. But here, let's assume that epsilon can be -1 in some nice region locally, and this basically says that if you use that practical actor-critic gradients, it actually gives like a linear, not linear in that sense, but it will improve as the number of iterations that you perform. Right. So now we have kinetic imitation learning and RL, both of them to predictable linear online learning problems. Now it gives us a reason of trying to understand whether we can use that PicCOLO to learn those. Right. So to give a more concrete example, let us consider a base algorithm which is mirror descent, which might be the one we are mostly familiar with. So what it does is that in here, we're going to use policy optimization. So the direction will be the the practical actor-critic gradient that I talked about, or the gradient from the imitation learning loss function. And here you have a Bregman divergence, which is a regularization about how far this pi is close to the pi n. So if the Bregman divergence is just like square Euclidean square norm, then you will get gradient descent. But so basically here you have to focus on two parts. One is the gradient direction, the direction you want to take, and the other thing is the regularization that you choose. And for now, you can think about the regularization basically is determining the step size for the problem. So if you look closer into this problem, this update rule, it actually performs 2 steps rather than 1. You have to first choose the regularization first. And the way you do that is you look into the current gradient or vector that you have, and you choose some step size. And after that, you use that step size to update your policy along that gradient direction. Right? So if you want to apply PicCOLO for policy optimization, we need to know how to define that gradient direction for the problem. Right? So let's go back to the previous reduction. So reduction says that we can apply this mirror descent on this new adversarial problem. So the gradient you will see is that the first gradient will be the prediction gradient from your model. And in this case, the predicted gradient can come in many different forms based on how you design those models. And here are some common examples that you might use. So you can, let's say you have a simulator. You have a dynamics model. You can compute a simulated gradient as that gradient, G and hat. Or another thing that you probably will want to use in, let's say, in simulation RL problems is that you can actually use off-policy gradients. Let's say gradient computing using samples from other policies. Or maybe you can use gradient computed by a replay buffer. So this is actually what people use in practice, just not in this way, but just as a direct way to update policies, right? But now we are treating that as a model gradient, not the exact one. And now, of course, we can also learn neural net or some other function approximator to predict that gradient as well, because we have a measure of true gradient when we do interactions. And then so we can actually learn that online or offline. So this is the first gradient. The second one we need to do is to compute that error. So the only thing that's missing is the GN, which is the one from the environment. And that one will be just the same as the active gradients or the imitation gradient that we have from the online learning part. So now we have definition of those. Now we can actually compare PicCOLO with other approaches that we know about policy optimization. So let's do model-free one. So the model-free one, what you do is that you interact with the environment with your current policy, you get the the gradient you care about, and then you just apply the standard mirror descent step. And that step can cover, let's say, natural gradient descent or trust region policy optimization and so on. And then so you use that gradient, you use that to decide your step size, and then update your policy in the direction of the gradient. Right. This is the most common thing. And there's another approach to do policy optimization, which is a model-based one. So in here, you interact with the environment, but you never use the GN to directly update the policy. You use that experience to update your model, and then you give you some model gradient. For example, this describes the approach of using replay buffer in RL. Right? You use that experience, update your model, which is a replay buffer, and then now you use the replay buffer gradient to update your policy. You never actually use the gradient from the environment directly. And then you can also think about this as a simplified version of like the model-based RL in terms of the optimal control approach, where they use more iterations in the both sides, but here we are simplifying that into one gradient step. But it turns out like this simplification retains like the most of the important structure and the property of the model-based approach. So these are two common approaches. Right. So next one is Dyna. Dyna is a very old algorithm proposed by Sutton. And so what it does is basically doing one model-based step and model-free step. So you call your model to give you a gradient and update your policy, and then you interact, get a true gradient, and update your policy. You just treat the model gradient as the exact one and just do the same thing. So you effectively doing twice iteration per every interaction. That's why it might be faster if the model is very, very well. So now it's PicCOLO. So PicCOLO has two parts. We're calling the first part the prediction step, and the later part is the correction step. So the main difference is that, let's say, compared with Dyna, this hybrid approach, the main difference is that in the prediction step, we do not change the step size based on the model gradient, as in Dyna, as opposed to Dyna. So this is the very first important difference. And the second important difference is that in the correction step, we're going to adjust our step size based on the prediction error, and then using that new step size to go along the error direction rather than the true gradient direction. So here we're going in the error, and then here you're doing the gradient on the left-hand side in Dyna. And of course, we can also use that experience to update our model. Right. So what happens is that when you choose step size and update direction in this way, you will basically increase your step size if your prediction error is small. If your prediction is well, basically means that you can trust the model more, so you can take a larger step size. So this is important, so because you are basically choosing step size based on the accuracy of your model. If your prediction is always well, let's say like a local linear problem, you can predict very well, you can take larger and larger steps. And then so that's like the intuition about why we want to use error to choose a step size rather than a gradient size. Another thing is that we're going to use the error to update the policy. And the main reason for that is that it's going to, when you update in the error direction, it can remove the bias of the prediction error that you have in the previous iteration, although you are not using the exact same step size. So they will not exactly cancel out, but they will just cancel out good enough so that it eventually won't have bias. Any questions? Okay, how much time do I have?
Well, it's 11:35, maybe 10 more minutes.
Okay, yeah, it's good. So let's try to visualize that a little bit. So let's say we have a cat learner, we're trying to go to the butterfly, right? So in the prediction step, you take the prediction gradient and go to that direction, follow that. In the correction step, you're going to see the true gradient and see the error, and now it's going to adjust the step size based on that prediction error, the error that you have, and go into the error direction, right? And now you do it again with the prediction step using the previous step size from the previous correction step, and they're going to this prediction direction. But because previously you incurred an error, so now it's going to travel a smaller step size than the previous one, which is 1, for example. Now do that again. Now you see another error, and because for now this is somehow lucky, so the prediction error becomes small. So now you have a smaller error, you're going to take a larger step size. So it's going to take larger than 1 step size to go through there, than the size of the arrow, right? And now, but let's suppose your model somehow is wrong. You give you a very wrong direction, which doesn't lead you to the goal. And so you're going to travel in that direction. Using the step size, you thought it's going to be nice because the previous prediction error is small. But in the next step, you're going to see the true gradient, which is going to direct back to the goal. And then now you see that large error, and then you're going to decrease step size and also travel in that direction back. And now you're going to use that to apply to the next prediction step and so on. Right? So eventually, we can prove the convergence in terms of average regret for all these approaches. So the baseline that we have is the model-free approach, just the mirror descent. So convergence roughly proportional to like the size of gradient, also the variance of the gradient. But it's going to be unbiased. At the end, the average regret converges to 0. And you have this model-based approach like Dyna as well. So in here, they are faster when your model is accurate, which means that you might have a smaller variance in model prediction, and also you have two types of iterations in Dyna. But the drawback of these approaches is that they will have a constant error, En, which is due to the prediction bias error. So at the end, the average regret will not convert to 0 due to prediction error. But in PicCOLO, what happens is that the En is moved into the numerator. So at the end, that part will convert to 0, even though the prediction is wrong. Right? But now, if you see that the gradient, the prediction error plus the variance of prediction is less than the size of the true gradient, which means that your prediction have a relative error less than 1, then this convergence rate is going to be faster than the model-free approach. So what it means is that PicCOLO can convert any base algorithm into a new algorithm that can use models, and it's going to accelerate when the prediction error is small, but it's still going to be unbiased in the sense of average regret, even when the model is wrong. So experiments. So we use that to wrap different base algorithms that we know work for RL. So we know Adam is okay, not very good, but okay. And then we know we can use adaptive gradient descent. It's like a natural gradient descent, but like with a step size that's like in the favor of Adam. And then we can also use TRPO. So there are some base algorithms that they fall into the family of mirror descent, and they can be used in RL. And then we are going to compare how they perform with different models. So we compare with the simulated models, simulated gradients, and off-policy gradient replay buffer, and even with an adversarial model, and to see whether like our previous claim about that being unbiased is true or not. So first we start a couple, which is simple, and it doesn't require too much time to run. So we run that with the base algorithm Adam, and then we compare that with different models. So the gray line is a base algorithm. They appear on the left-hand block and the right-hand block. So it's actually more visible on the right-hand side because that's overlapped together on the left-hand side. And another thing we want to compare is the red line, which is the one using the true dynamics as a predictive model. And that true dynamics, doing the dynamics is true, but that model doesn't have a 0 prediction error in this sense. But it's a meaningful direction. So you can see that the red line, if you have prediction that's reasonable, is faster than the gray one. Now, let's compare with how Dyna and PicCOLO responds to a very wrong model. So on the left-hand side, we have a model that's computed by using a randomly initialized neural net dynamics. So basically, that prediction doesn't give you much information, right? So you see that in here, the blue line will converge to the optimal ones without much bias. But at the end, the Dyna version, the green one, will fluctuate a lot. So that's the bias that we have in the regret bound in Dyna. But now let's even go to the even worse scenario. So let's consider an adversarial model for some reason. So the adversarial model will give you a gradient, which is the negative of the previous true gradient times a very large constant. Yes, it's going to crash you. And you can imagine that Dyna in here, it completely fails. It can never learn because basically you have large error and then just crash, right? But in here, PicCOLO converges, but it's slower than the model-free approach, right? This corresponds to here. So if your prediction error is large, it will not be faster, but it's still safe. You also converge, but slower, right? So something like this. You have nice model, you converge faster, but if you have like very wrong model, like adversarial one, it still converge, but slower. So now let's look into more complicated setting than couple. So here we're comparing natural gradient descent and TRPO as base algorithms. So those are the gray lines on the left-hand side and the right-hand side. So you'll see that, and now we have different models. Like we use the samples from the last experience, and also we have a replay buffer from like I think 100 rollouts from the previous experience, and also have this model from the true dynamics, and to try and see whether PicCOLO can improve, because these are like somehow like reasonable models that we thought of, right? So we see that when you PicCOLO that, it will converge faster, let's say in this environment. Also try that in other environment, let's say in this work of 3D, and then the color lines, they are colorful, so they converge faster than the monotone gray line, right? So we have some preliminary results about showing that we have theoretical bounds, right? But those might not be tight enough for practical purpose. But that gives us a direction about why PicCOLO will work, right? But now in some experience, at least in the OpenAI gene, we show that empirically that PicCOLO actually kind of satisfies the theoretical property that we want, right? So what we show is that we provide a reduction-based framework that can convert any base algorithm that the thing you'll probably be using to a new algorithm that can use model information. So you can think PicCOLO is an unbiased way to use, for you to safely use like models, like off-policy gradients and replay buffer, for example. That's typical examples. And the important part is that it's going to adaptively use those. So it's going to be optimal to the prediction error that you will have. And eventually it's going to be unbiased. And that's quite important. So in conclusion, for today's talk, so we show that positive optimization is predictable in some sense, because the loss function shares some information from the past loss function. So some information can be inferred, and especially in the formal predictive model about predicting gradients of the future. And we'll show that this means that the previous approach, the adversarial treating of those problems, is going to be suboptimal. There's a need for us to develop a new algorithm for that regime. And here we show a particular algorithm to use predictable information, the PicCOLO one. And it's actually a meta-algorithm, not an algorithm. It's a meta-algorithm that can reuse previous approaches. And then we also show that if we consider those information, it will give us a tighter bound in analysis, right? But there are so many open questions when we just discovered this, right? So this is nonetheless limited to policy optimization. And also, like in here, I think the current version of PicCOLO is not the best use of predictive models. Let's say your predictive model is exactly correct. Like in the first beta leader, like conceptual algorithm, it can solve the problem in one step. But here it cannot, right? So how do we actually better use those models so that it can actually convert even faster than the current conversion that we have? And also, like in here, PicCOLO, our analysis is focusing on static regret. But in here, another idea is that we can move to dynamic regret or adaptive regrets. And that will actually tighten the bounds that we have to convert the regret bound to the performance bound. It's similar to that 2 epsilon that we talked about in imitation learning. Yeah, so this concludes my talk. I want to thank my collaborators. So we have Xinyan Yan and Nolan Wagner from our lab, and also Evangelos Theodoro from Georgia Tech, and Byron Booth, my advisor, and also Nathan Radley from NVIDIA. Yeah, so any questions?
Time for maybe 1 or 2 questions.
So I'm thinking of the first 1/3 part of the talk.
Mm-hmm.
So a lot of the reason the predictable online learning problem came up in the imitation learning setting was because you were constructing these phi-n's to get at the state distribution mismatch, right?
Mm-hmm.
Could we try to get at that state distribution mismatch directly? The fundamental problem there was an expectation of a state visitation under d pi
Yes.
that we needed to get it, and rather than constructing a bunch of surrogate phi-n's to get at it,
Mm-hmm.
can we instead directly go at the off-policy mismatch between d pi behavior versus d pi of the policy?
I think, so for example, I think you cannot do that if you only have samples, but if you have a dynamics model internal simulator, you can do that. Because when you have that knowledge, if you can do simulations in some sense, you are actually having a way to define that capital F. And then just by querying that oracle, you can basically know what you will actually perform in the real environment, so without really doing any interactions. But if you only have, let's say, just samples collected from different policy without really constructing a sense of model from them, then eventually, I think you might be able to do something like averaging in some sense, like weighted average, so that you can approximate that. But it won't be perfect, but maybe that'll be good enough. So actually, you can think that as a predictive model, let's say just like the thing I talked about using off-policy gradients and off-policy replay buffer, as predictive models, right? But if you just use that directly, you have bias because that's not going to be perfect. But that can actually be combined inside the PicCOLO framework and then just to make a safe use of them. Does that answer your question? Okay.
Anything else? Right. Well, we're right on time.
Okay, thank you.
Thanks for speaking again.